will not be that bad. And the subject of my talk will be the recent paper describing the monitoring of M87 throughout 2009-2017. So what can we learn if we use old data and analyze them together with more recent new data, and we try to formulate some conclusions about this interesting object. And that's the project that was done by many people. Actually, there are like over 200 people involved, and some of the most involved people you can see on this first slide. And the object I'm talking about, it's now it's kind of a popular object, so most of the people are familiar with the M87 already. This is the view from the Hubble Space Telescope of the galaxy M87. And sometime about 100 years ago already, people noticed that from this galaxy, this little fluffy cloud on a sky, there is this jet emerging. So there is this sharp, narrow structure coming out of, let's say, some kind of a core of this galaxy. So this is the view in optical wavelengths. And if you look at it in radio wavelengths, you can learn more about that. So the first image, the one to the left and up, you can notice here that there are those two lobes of radiation. So this helped to understand what this jet could be, and the understanding is that this is a collimated outflow from the center of the galaxy. The magnetic energy turns into kinetic energy. At some point, it hits some kind of cloud of matter, and then this kinetic energy turns into radiation energy. So this is why you see those two lobes, but you only see one narrow jet. And the reason is that the counter jet, this is what you see is the jet going in our direction, and the counter jet is strongly deboosted because it's fast, and Doppler effect is telling us that the brightness of this feature will be limited. But once it hits this distant cloud, you see this lobe of radiation, the cloud in the left bottom side of this first image. So when throughout many years, developing better and better radioastronomical observatories and going to shorter and shorter wavelengths to break the diffraction limitations, we are able to go deeper and deeper. So if the first image, the scale that you are seeing is thousands of light years, then the last image, this donut of M87 published by Event Horizon Telescope, now we are talking about the resolution of light days. So this donut is not on scale of 1,000 light years, it's on a scale of just a few light days. Okay, so this is the observation that EHT published last year. This is some background data on this object, and one number that I really like is the diameter of this feature. By the way, okay, this is 42 microarc seconds now. And comparing it with something more familiar, like the diameter of full moon is kind of, people know what is the angular size of the moon. Most people have seen the moon. So this diameter of this object, as seen, as observed, is 45 million times less. So it's really, really a tiny, tiny little donut on the sky. Okay, and performing the analysis of this object, trying to interpret it in the framework of GRMHD simulations, we build up an interpretation of that. So there is this forward jet, which you have seen in the previous images, and we understood that this black hole needs to be rotating and that the spin needs to be pointed into the page. And we assumed here in this analysis that the spin is aligned with the jet. So this accretion structure is not tilted with respect to the axis of black hole rotation. So because of that, we understood that only this configuration will allow you to see the boosted bright side at the bottom of the image, and this is what this interpretation is based on. And it also means that the rotation of the gas as projected into the plane of view, this should be the clockwise direction. And I will play a little simulation for you. So this is what happens if we take GRMHD simulation, align it the way we understand that M87 is aligned in space. You've seen this narrow ring. I will actually replay it. So there is this sharp narrow ring, and this is actually the trace of the photon orbit, but there is all bunch of this fluffy turbulent stuff around. So this is the direct emission of the accretion flow. Now we are looking at it with the resolution of the EHT, sorry. So this is what EHT could hope to see at best. If everything works with the instrument, if the telescopes behave well, this is the best we could do. We cannot go currently to higher resolution than this blurred blob. But you can notice that in this blob there is a lot of dynamics going on. So you see these bright components appearing, and this clock and is tracing the maximum of the fitted maximum of the flux. So you can see that we can say quite a bit about the dynamics of this flow. But what you can also notice, this is the time passing. That was 1 year of life in M87, this whole animation. So you can see that during 7 days, which is how long a single year campaign can last, there's not much changing on a time scale of a week, because week is just, I start, let me start from here. Okay, that was a week, not much changed. But if you look for a year, things are changing. So that means that we really need more than one observational campaign, more than something that we can do during 1 year. We need more years, because next year, this orientation of these blobs will be different. And that could help us to learn about the dynamics of this accretion flow. So that's the idea behind, background idea of this study. Very briefly, to tell you about the method that we can use for this extreme resolution. The method is called very long baseline interferometry. This is kind of pushing radio astronomy, radio interferometry to the extreme, because we knew before the distance to M87, to the central black hole of M87, we had some information, some priors on mass based on different studies about the dispersion in stellar dynamics. So we knew that we would need a resolution about 20 microarc seconds. And if you do a simple math of the diffraction limit, which is just a wavelength over the size of your telescope, it will tell you that you need 10,000 kilometer baseline, which is about the diameter of the Earth. And you do need 1 millimeter wavelength, which is again pushing the radio astronomy to the extreme. Actually, before this image that you see here, the M87 image from EHT, there was not a single VLBI image in 1 millimeter. That's not the first observation of resolved structure of accretion flow near the black hole. It's also first image ever done with VLBI in 1 millimeter. There is a lot of technical difficulty to get to this point. So here you see this example, 2 telescopes separated by about the diameter of the Earth. So we actually, in 2017, we had 7 telescopes looking at the M87, but only in 5 geographical locations. So that gives us 10 pairs of telescopes, which gives us 10 measurements. 10 measurements are of course, not enough to construct anything like this reconstructed image. So we are playing another trick here, and this a very smart trick is observing that the Earth is actually rotating. So as the Earth is rotating, the geometry between two telescopes and this distant point in sky, M87, it's changing, meaning we are sampling different and different spatial frequencies. This is interferometry, so we are sampling Fourier components of the image, not the image itself. We are probing so-called complex spatial frequencies. Okay, so in order to study the dynamics of this object, we do need a couple of years of observation. So since we don't have anything published outside of after 2017, what we could do for now is to go back to the old results. And M87 was observed since 2009 with VLBI EHT prototype arrays. So this is the configuration of the first such prototype array that performed observations in 2019. And in 2012, we had this paper about these observations that for the first time we have resolved this feature, meaning that it's not a point source anymore since 2012, that we see that there is some structure. But of course, there's not much of this structure. This is continuous line is the fitted Gaussian blob, and dashed line is the fitted ring. Based on this information, based on this observation, there was a claim made in 2012 that excluded retrograde spin because it compared the size of the object in the sky to what would ISCO of retrograde accretion look like. So that didn't age so well, because we now know that this size is not really sensitive to the ISCO size. It's really sensitive more to the size of the lensed photon orbit. And this is also being disputed. There is an ongoing discussion in the community about what can EHT at the moment say about the size of the lensed photon orbit, given all the astrophysical uncertainties that are there. So this is just an example of those astrophysical uncertainties. You see a panel of averaged snapshots from GRMHD simulations, and you see different spin values. And you see different R-high parameters, which is a kind of a plasma parameter, which is telling you where is the region in the accretion flow that is emitting most radiation. And you see that it has a lot of influence on what you would see on average. This sharp bright ring is this part corresponding to the lensed photon orbit, but it's only so bright here because it's constructively adding in the average, while this turbulent feature of a direct emission is not adding constructively. So this is not what a single snapshot would look like. This is what you would get if you averaged 1,000 or so of snapshots. The EHT is currently more sensitive to this direct emission, and you can see that for a large negative spin, this stuff around the sharp ring, it has large radius. And if you go in the direction of large spin, large positive spin, and higher R-high, you see that this direct emission can be very small. It can be smaller also than this photon ring. So this is all these uncertainties. While we know that the ring should be 40 microarc seconds in diameter, and this is difficult to dispute that, there is a lot to dispute about this astrophysical interpretation of that measurement. Okay, so that was a comment and 2009 observations. We repeated the same configuration observations in 2011. They were calibrated, analyzed a little bit, but never published. Then in 2012, we still had a similar array, but there was a nice progress happened. And that progress was, this is the publication related to that, published in 2015, that progress was that for the first time we were able to measure closure phases. And I will make a very short comment about the importance of closure phases. I mentioned how 1 millimeter radio astronomy, especially VLBI, is very complicated. This complication to a large degree comes from the behavior of the atmosphere. So atmosphere is very bad, very turbulent, and it influences hugely those measurements. Actually, to the degree that we can never get an absolute phase. Forget about it for millimeter VLBI. You can never work directly with visibility phases. But there is a very smart algebraical trick that you can go around a triangle of three stations, some phases measured at those three baselines, and then if you add them in the proper order, you will cancel out the station-based influence that should cancel out the influence of the atmosphere at a single particular station. And these are the closure phases which are this very robust type of measurement. So if we get them, we are very happy, because that means we have well, an important information that is not subject to corruption from the atmospherical effects over the sky, over a single telescope. It is nevertheless still very tricky to get phase measurement at each station. What you see here, left panel, the red curves is what you get from the atmosphere. All this corruption, all this wrapping of phase is related to the turbulence in the atmosphere. And we have to play a lot of sophisticated games with these measurements in order to recover phases as smooth and nice as you see in the right panel. We expect them to be constant on relevant timescales, that the source is not changing on a timescale of 400 seconds. That's what it is telling you, the behavior of the red curves in the right panel. Okay, this is a pretty plot that I will skip for the sake of time, and I will move to the 2013 observation. So when a telescope in Chile joined the array for the first time, which, as you see, it gave us this very long baseline between the US and Chile. So these data were also calibrated, but they also were never published. And the reason was that everybody was rushing to improve the array and get really this improved stuff that allowed to publish the image of a black hole. So although these results from 2013 were kind of interesting, people were too busy preparing for the next editions, and nobody had really enough time to properly work on this data set. Nevertheless, some reduction was done, and you can see the visibility amplitudes that we have measured, and you can see the best Gaussian fit to those. You can also see that this Gaussian fit can not in any way explain what are these guys doing, what are those very long baseline measurements. So this is the plot that I found on some internal server of the EHT. And there was a comment added to that made by Michael Johnson in 2015 that the apex detections, those long baseline guys, they clearly require a more complicated model. And Michael didn't specify the model, but of course he had in mind something like that. This is what it would look if the source was not a Gaussian blob, but a ring instead. So the visibility amplitudes of the ring could easily explain this growth of the flux for very long baselines. All right, so this is 2013. In 2017, you know the story. We had this large array and we got much more data. And if we look, this is the, where do we sample in the UV plane? So everything gray, these are the visibility amplitudes that we did obtain in 2017. And all these old data sets are points that are shown with colors. So you see how extremely sparse it is between 2017 and the old data sets. Those old data sets are not enough to produce unconstrained images of the source. But what can be done, maybe you could model out this source under certain strong priors. So this is all the amplitudes, all the visibility amplitudes of the past data sets. And I will spend just a minute explaining what can you see in this plot. By the way, I also remember 1 year ago sitting in Opava at the lecture of, I will not mention whose lecture, but I remember working on this plot a year ago in Opava. So now it's all, you know, a circle. Okay, so if you look at it, first of all, these dashed lines. This is the analytic Fourier transform of a thin ring. This is just to guide the eye. The gray dots, this is what we got in 2017. The gray dots with the envelope, with the black envelope, oh, sorry. Those are what would we get if we sampled 2017 data with the sampling locations of the old observations. Okay, and now I will point out two interesting features that you can notice. First of all, if you compare what you would expect based on 2017 data, if you go back to the past, what you would expect to see, you can see that for short baselines, the left arrow, you have an agreement between 2013 and what you would get with the 2017 model. So the gray points with envelope are around the same amplitude of the karma SMT measurements from 2013. But on the other hand, if you look at the long baselines, the right arrow, you will see that there is a large discrepancy between what you would expect and what you actually measured in 2013. So what it means is that something changed in the source, and it wasn't a simple change that everything is brighter or less bright, because then everything would be growing by the same factor. But short baselines didn't grow and long baselines grew, but by a factor of 2. So there is some important structural change in the source between 2013 and 17. Then there is another thing to take a look at. If you sample 2017 model with the old sampling, you can see that some of those points, the gray points with black envelope, they go very, very low with the flags. They are sampling a deep visibility null. But those same points, but actually measured in 2011 and 2009, for instance, they have much higher amplitudes. They are not very deep in this hole, in this null. They are much higher, more than an order of magnitude higher. So what it means is that, again, something had to change structurally. If there was a null in the past, then this null was clearly not at the same location. Okay, so now we can try to model our source, but what model do we choose? This is 2013 data, and here we fitted the ring. But here we fitted an asymmetric Gaussian. It also fits well. And it turns out that if we didn't have these high spatial frequency points to the right, the cluster to the right, we could also fit a ring that would be twice as large. So there is a lot of degeneracy here, and we cannot say that this old data can provide us with the information of this source structure without a strong prior. But is the prior justified? Can we say that, well, what if it's a ring? Well, we would say that this is the justification for our strong priors, this kind of unambiguous detection of a ring in 2017. So now we kind of feedback this information, meaning we are not using Gaussian asymmetric models. We are making an assumption that there is, but that the source is kind of circular. That is our main prior. And the model we are using, the main model we are using, is a very, very simple model of a ring. It just has 5 degrees of freedom. So this is this sort of geometry that you see to the right. It only has a bunch of parameters, 5 degrees of freedom and 2 degrees of freedom to capture large scale flags, because our measurements are sensitive to brightness in the distant jet, unfortunately, at least some of our measurements. So 7 degrees of freedom, still not that much. Still, there is a hope that this model could tell us something about source geometry and not violently overfit or underfitted. I will skip this little explanation. This is just showing different aspects of what we are doing, the observation, the GRMHD, blurred GRMHD, to show how similar it is to observation, and actually model fitted actually to the GRMHD simulation to show that it's kind of similar. We did first perform tests on synthetic data in order to justify that this modeling makes sense at all. This is the bunch of simulated synthetic data sets that we used to test numerically all this developed approach. These are the results that we got using synthetic version of 2009 array, 2011 array, and so on. So what is to see here, it's mostly that consistently, even these very, very sparse measurements are allowing you to constrain the size of this object. And this is quite constrained quite well, meaning that we, at no place we have stuff that is twice smaller or twice as large as the real thing. So this is good. The orientation is constrained, not so great, but not terribly. So there is some hope that maybe if we apply it to the real data, maybe it could actually not be so crazy to constrain some geometric parameters. These are just the marginalized posteriors from the synthetic data. And what to see here is a dashed line in the left column. This is the diameter of the lensed photon sphere. So this is somewhere about what you maybe should get up to some kind of astrophysics related uncertainties of the model. And you see that those posteriors do overlap. They are not terribly wrong. And in the right column, the dashed line is what you, in principle, what you, well, should get. So you see that these posteriors are not great. 2013 is not terrible. 2012 is maybe not always terrible, but 2009 and 2011, they basically are kind of bad in constraining the orientation. Okay, so we think now that we could, in principle, learn something from applying those simple geometric models. So we tried to do that. This is the results of fitting to the actual data. Right. So what I did plot here are the uncertainties in the position angle. So you see that those uncertainties are large. Not only they are large, our data do not allow us to break the degeneracy between the orientation and orientation plus 180 degrees. So really, we are only constraining the direction of this anisotropy in the flux, but we are not really able to say whether the flux is like in 2013 is the maximum to the left or to the right. But we know it's not to the top and it's not to the bottom. Okay, so this is these are direct fitted models, max likelihood estimators. Then we have the blurred version, blurred to the resolution of the EHT. So that is something that should look more or less like the observation we could make with a larger array. And then we have the mean, which is just mean of the images in the posterior volume. This is like 20,000 images averaged. And there is another model that we used just to validate these results, not to have too much of a model bias. So this is the model that can degenerate to a Gaussian. And you see that if we allow it to degenerate to a Gaussian, not always you can be so certain that there is this central darkness. For instance, the 2009 results are fine with putting a lot of flux in the middle of the ring. This just means that your data is not strong enough to say that this Gaussian mode can be excluded. But you also see that 2013 is strong enough to exclude the Gaussian mode, which means that 2013 was probably, it's fair to say that this is the historically meaning when the observations were made, the first data set that really sees this shadow of a black hole, meaning the central depression of flux. This is the snapshot from the outreach materials that we prepared for the associated paper. And here you see where is this 42 microarc seconds ring in all the max likelihood fits. What are the uncertainties of the position angle? And you also see how the models compare to the images. So we only have images in 2017. The other data sets were too sparse to get as the images. But you see that the orientation in the images is kind of consistent with those models. Those models are simple, but they are not very dumb. They are a little dumb, but they are not terribly dumb. They can tell you the diameter and they can tell you the orientation of the position angle just right and consistent with the more sophisticated imaging methods applied in 2017. Okay, so these are the posteriors of diameter and of the orientation. Oh, I see. I'm very sorry. I see actually there is no labels on the horizontal axis, so you'll have to trust me that the gray area in the left plot spans between 39 microarc seconds and 45 microarc seconds, which is the uncertainty in the diameter of the ring reported by the EHT in 2019. And you see that all those posteriors from the past are consistent with that, meaning they do not exclude this region reported in 2019. What it means is that, well, the size of the ring was consistent between 2009 and 2017. On the other hand, position angle, it seems that it varied quite a bit. These are the posteriors of the distributions. I wanted to use them to highlight some uncertainties, like the fact that there is this ambiguity of 180 degrees. So those posteriors look periodic. And you also see that, for instance, FW is the thickness of the ring. You can see that it's terribly unconstrained in 2009. Then in 2013, you see that you still have 180 degrees degeneracy, you have two blobs instead of one, but you also see that you are starting constrain things like thickness of the ring right now. And then 2017 is just like the dream of people doing modeling, because everything is super well constrained. So all the uncertainties here are not really coming from the uncertainties in the measurements, they are coming from uncertainties of the model, right? Because it's one thing to show that your what are the uncertainties in posterior of your model. The other thing is to argue that your model is the right model to use. There are systematic uncertainties associated to that. Okay, and I have 3 minutes if I understand correctly, so it's great because I will just quickly go through the some of the things we have learned from this exercise of fitting the old data. So the first question, what would happen if we would really argue that, well, maybe it is an asymmetric Gaussian after all, and maybe that's a better model? Would we get some sort of consistency in the best fitting max likelihood models? So it turns out we would not, meaning we would have to find a physical explanation why this core of a galaxy is changing dramatically from year to year. And well, theoreticians would find an explanation for that, but nevertheless, I would say that this is doesn't look as good as a consistent diameter of a ring. Of course, this is a little bit of choice being made here. What you say that your prior, what is your physical prior that you apply when you analyze the data, but this doesn't look convincing. If I see so that, I wouldn't be convinced that this core can indeed be a Gaussian. Then another thing we have learned is we tried to parameterize, measure from the GRMHD simulations how much can different models of GRMHD vary in terms of this position angle. So what you see here are histograms from different GRMHD simulations, and you see the measurements of the position angle in the past coming from the EHT. And you can see that some of those histograms do not overlap with the measurements, meaning it's difficult to explain this sort of variation in the position angle of this brightness of the crescent with this particular GRMHD model. So it seems that once we have more observations, we will be able to start excluding different models, numerical models of the accretion based on how much variation they can predict. And the last thing that I wanted to comment on, I think, is a following problem. The core emission of the M87 is changing from year to year. It's not quite constant. Actually, it changed between 0.5 Jansky, so the third column here, and 0.9 Jansky across last decade. The question is, if you do a radiative transfer, if you scale everything, and the opacities will change, and of course the regions where you see the brightness will change in some complicated fashion, more complicated than just scaling the entire image by a constant factor. Would this measurement be robust against that? And it turns out that, yeah, actually fitting rings to models is robust against this sort of change of total brightness. At least between 0.1 Jansky and 1 Jansky, we don't see a lot of influence of the total brightness. So we are safe from the effects of opacity. Okay, and this is my last slide, apart from the thank you very much slide. Just couple of comments. The most important things are that we did confirm that the old data are consistent with the model of a ring of particular size. And we also see that the diameter, that the position angle of the bright side of the crescent was varying across both years. And from this variation, we can perform some kind of tests of the models that we are trying to understand the source with. Okay, thank you. And the paper is available. Please take a look if you're interested.
Thank you, Maciek, for your very nice contribution. And I would like to ask the audience to ask questions. So raise your hands.
I'm raising my hand.
Yes.
It's not a question, it's a request. And actually this is to many speakers. I didn't read the conclusions fast enough. Would it be all right if the speakers left us with the conclusions at the end of their talks? Thank you, Maciek.
That was easy.
So another question. Oh, here. So Deepika, Ananda, please. We don't hear you.
Maybe you can type in the chat. I think we have some.
Maybe a question. Oh, yes, exactly. It is typed.
Oh, let me see.
Oh, it is a.
I have a question, but I don't know how to raise my hand.
Yeah, Ronaldo Vieira, I have a question. and we can hear Deepika.
So Ronaldo, maybe you can ask, and in the meantime, Deepika, if you have problem with your mic, maybe you can type your question.
Yeah, that's better.
So can you hear me?
Very well.
Yeah. Oh, hi, Maciek. I have a question about the model of the source. I mean, some people worked with the hypothesis that the source is not a Kerr black hole. For instance, a superspinner or something like this.
Yeah, including myself.
Including you, yeah. So what are the constraints that those new data put on alternative models?
Right. So in terms of these sort of studies, I'm afraid that those old data cannot contribute much. In terms of, well, this being a trace of the photon ring, but in a different space-time. So because those data are much sparser than 2017, I don't think they contribute much to that discussion. The kind of models that they can constrain are, for instance, the models where you say that, well, maybe you were just lucky guys and you saw this ring as some kind of a transient feature in the jet. That can take pretty much any form. So maybe you were very unlucky and it happened to look kind of like a ring in 2017. So this persistence of this feature in the same geometry means that this is unlikely. But testing non-Kerr metrics, I wouldn't go to that.
Thanks.
Okay, great.
I'm sorry, maybe in the future.
Okay, and now Deepika have typed her question here. Do you see it, Maciek?
Yeah, I'm wondering if the tilted disk model, I will read it out loud. I'm wondering if the tilted disk model for M87 could be responsible for the transient feature. So we actually started looking into tilted disks simulations. The time scale for this precession stuff that could add another time-dependent component is much longer than this decade of observations. So it wouldn't, I don't think it could influence in a sense that it would add some non-steadiness to the image. However, it definitely could influence the average image, meaning that if you allow for the tilted disk model, then you have these 2 additional degrees of freedom because you have to constrain the spherical angle between the jet and the spin of a black hole. And actually those 2 additional degrees of freedom can allow you to get whatever you want in terms of position, in terms of average position angle. So yeah, so this is something that we will need to investigate more in the future. Currently, we can only work and formulate constraints assuming that it's not tilted.
Okay, thank you, Maciek, for your replies and for the questions. And I think we can.
May I ask one question also? Maciek, may I ask you about Sagittarius A star? So you say that there is high variability, and is there any way to get the image of Sagittarius A star?
Absolutely, yes.
Okay. Can you comment something? Say how fast we can get the image? And
okay. Let me make maybe a little bit wild guess that will maybe bite me a year from now. But I would have a hope to speak about Sajay on next RAGtime.
Okay, so we are very close. Very good.
Okay, thank you, Maciek.